Now that we've finished looking at different ways and tools of differentiating functions, we can now look more deeply into the applications of derivatives. So the very first thing we're going to look at is extreme values of functions. This means we're looking for the largest y value or the smallest y value in some interval. These are called max and min values of a function. In particular, we're going to call them absolute minimum and absolute maximum if they are the extreme values of a function. So these extrema, which is plural for extremum, can occur at points in the inside of an interval, or it could also be on the endpoints of an interval. Let's take a look at some examples to see what that looks like. So for parts A, B, and C, we're going to use this first graph. We're going to look for the absolute extrema between -4 and 0, included -4 and 0. And the largest y value is going to be at 2, located from x equals -2. So that's your absolute maximum here. The smallest y value will occur at 0 at x equals -4 and 0. It's okay if you have two absolute maxes if they are the same y value, or two absolute mins if they are at the same y value. So your absolute max occurs at 2 when x is equal to -2, and then your absolute min is at 0. And this is when x is equal to -4 and 0. Let's take a look at a different interval. We're going to include -2, but this time we're not including 0. This means that before, when we had our absolute min here, we counted that as an absolute min. Because we are not including 0 this time, there is no absolute min. But we'll still have an absolute max because -2 is included. So x equals -2 is included. Our absolute max is at 2 when x is equal to -2. And there's no absolute min. For C, we're not going to include -4, and we're not going to include -2. That means we're not going to have any extrema here, because we can't include the lowest y value, and we can't include the highest y value because it's not a part of our interval. So this just has no absolute max or min. So this first graph is a continuous graph. What happens if we don't have a continuous graph? And now we're going to look at D. So we're looking for extrema between -4 and 0, including -4 and 0. Well, we do have minimum values. We have two absolute minimum values because the y value is 0 and x equals -4 and 0 are included in this interval. However, if we look at the max, we want to say it's going to be 2, but that's not actually part of this graph. At x equals -2, the value is actually 1. So in this case, we don't have an absolute max, only two absolute mins. So your absolute min is 0, and this is when x is equal to -4 and 0, and there's no absolute max. So if we look at the pattern here, the only time when we had both the max and min is in question A, when we had a closed interval and a fully continuous graph. So those are the two things we need for this case for there to be both a max and a min. So it needs to be continuous over a closed interval. Now, this is not always the case. It's just the case for example 1. A theorem that we need to keep in mind, because we will use this, the extreme value theorem, states that if f is continuous over a closed interval ab, then f has both a max and a min over the interval. So if you have a function and it's closed and continuous, you will be guaranteed to get a minimum and a maximum in that interval. However, the other way does not work. If f has both a max and min, it doesn't mean that f has to be closed over an interval and continuous. Okay, so you could still have a max and min in a graph that is discontinuous or have an open interval. So just keep that in mind, only works in the one direction. So we just talked about absolute extrema. There's also relative extrema. You could also call this local extrema as well. So these extrema usually occur when there's an open interval, and it's not the absolute max or the absolute min, but it looks like it's a max or a min relative to some interval. So relative extrema exist when the value of the function is larger or smaller than all other values relatively close to that value. Let's take a look at example 2 to see what that actually looks like. So for this first graph on our left side, we're looking for a local max and a local min. In this picture, what we see, this looks like a local max or relative max. But is it an absolute max? No, because there are going to be higher y values in this function. Then your local min looks like it's going to be down here. Is this the absolute minimum? No, because there's lower y values here. But when we look at this interval, it looks like these are max and mins. So your relative extrema here is going to be at 0, 0 for your local max, and 2, -4 for your local min. And if we think about the value of the derivative at each of these local max and mins, your tangent line here is going to be 0, which means your slope here is 0, and that also means your derivative is 0. So if this function is called f, the derivative of f at x equals 0 is going to be 0, and the derivative of f at 2 is also going to be 0. Looking at the next graph, it doesn't look like we have a max at all. It looks like our graph is just going to continue on. And remember, this is an open interval. We are not including the endpoints here in this interval. So if it's an open interval, all we really see is a relative min or a local min. So 1, 0 is our local min. Now if you look at the derivative at x equals 1, the slope here is non-existent because we have a discontinuity, and this is called your corner. So the derivative of f at 1 is undefined. So what do we notice here? We notice that we're going to have a local extrema whenever our slope is 0 at that point, or derivative is going to be 0 at that point, or undefined. So that is what a critical point is. A critical point is some value at c if f prime c is 0 or f prime c is undefined. Then this is called a critical point of f. So that means x equals 0, x equals 2 is a critical point of this graph on the left side, versus x equals 1 on the right side is a critical point for that absolute value graph. So your relative extrema only occur at critical points. So that means if f has a relative max or a relative min at some x value equals to some number, that number is a critical point then. So let's take a look at a graph that has absolute maxes and absolute mins in there, and also relative max and relative min, or local max and local min. So your absolute minimum is the lowest y value you can find in the graph, which is down here on our left side. Your absolute max is the highest y value you can have in the graph, and that's on our right side at x equals c. Now, you have a local max and a local min as well. At x equals a, it looks like we have a max, but if we compare it to x equals c actually has a higher y value. So this is a local max. It's not the largest, but it looks like there is some high y value in relative to some interval, and similarly with the relative min at x equals b. So take a note again that these relative extrema only occurs at critical points. In this case, your critical points is going to be x equals a, x equals b, and then your endpoints are included in there as well because we need to check the endpoints. So absolute extrema in this case occurs at critical points or endpoints. So to keep those two things in mind, when you're looking for relative extrema, that means that at that point, your derivative is going to be 0 or undefined. For absolute extrema, this can occur at a critical point. So again, if your derivative at that point is 0 or undefined, or it could happen at endpoints. So keep this in mind every time you're trying to find extrema. Now, this is all fine and dandy if we have a graph. If we're given a graph, it's fairly easy to see what the absolute max and mins are and the relative or local max and mins are. When we don't have a graph, we can still find these relative max and mins and absolute max and mins. We have a test for that instead, and we're going to use algebra to determine that. Before we move on, I go through the 4-3 guidelines on how to find relative and absolute max and mins. Just because the derivative is equal to 0 or undefined, it doesn't mean there is a max or min there. Okay? So take a note of that. Just because there is a critical point, it doesn't mean that there is a max or a min. We need to check. And we're going to use these guidelines to check. The first thing you want to do is find a critical number on some interval. And we do this by setting the derivative to 0 and seeing when x is undefined. These are your critical points. And then the endpoints also are candidates for extrema as well. We're going to evaluate each candidate by plugging the numbers into the original function to find out their y values. The smallest y values are going to be the absolute minimum. The greatest y values are the absolute maximum. So the critical points are x values, and your max and mins are y values. In other words, if we're going to use 270, the point 270, and we know it's a relative minimum, that means that the minimum of the function is 70, and this occurs at x equals 2. So that's how we should state our answers like that. The minimum of the function is something and occurs at x equals something. Now let's take a look at example 4. So we want to find the absolute extrema for f of x. F of x is 3x to the power of 4 minus 4x cubed, and we're looking over the interval of -1 to 2. So if we look at the very first step, it says we want to find the critical numbers of f on this interval. And we are going to do this by saying the derivative equals to 0 and to see when it's undefined. So our first step is finding f prime of x. We're going to use our power rule here. So bring down the 4, multiply it with a 3 is 12. Subtract 1 from the exponent. Bring the 3 down, multiply by -4, so that's -12, and then minus 1 from the exponent, so you're left with x squared. Now if we take a look at this function, this is a polynomial function, and it's never going to be undefined. So then our next step is to set this equal to 0 and then solve for it. So 0 is equal to 12x cubed minus 12x squared. We see a 12x squared in common between those two terms, so I'm going to factor that out. And then now we can solve for x. So x is 0 or 1. Now our next step is to see what the y values are at each of those critical points. So I'm going to evaluate f of 0, f of 1, and also the endpoints as well. So again, that's f of -1, our endpoint, f of 0, a critical point, f of 1, and then f of 2. So if I plug -1 into the original function of f, we get 3 times -1 to the power 4 minus 4 times -1 to the power 3. This is 7. And then f of 0, that's 0 minus 0, which is 0. F of 1 is 3 minus 4, which is -1. And then f of 2 would give us 16. So if we take a look at our y values, our largest y value is 16, and this occurs at x equals 2. And that is our absolute max. And then our lowest y value is -1, and that's our absolute min, and this occurs at x equals 1. Take a note of how I'm writing out the solution. They're very picky for the AP Calculus exam about how you word your final answer. So don't give it as a point. Say your absolute max is, and then your y value at x equals some number. Let's do another example. So for example 5, we're going to get another function that's 2x minus 3x to the power of 2 over 3 over the interval of -1 to 3. So we're going to find the derivative first. The derivative of 2x is 2. Then the derivative of our next term, we're going to bring down the 2 over 3. So we're left with -2 in the front, and then -1 from the exponent. So 2 over 3 minus 1 is -1 over 3. Now we can rewrite this as 2 minus 2 over the cube root of x. Just changing into a radical form. Now we're going to set this equal to 0, and we also take a note of when this function, or this derivative function, is undefined. So we'll take a note that undefined when x is equal to 0, because we can't have 0 in the denominator. Now we're going to see where our critical points is when we set f prime of x to 0. And then we're going to solve, or try to solve, for x. Now I'm going to move the 2 to the other side. And then divide both sides by -1. Then I'll divide both sides by 2. Then we can cross multiply. So x is equal to 1 in this case. Now we're going to look at finding our y values at each critical point and the endpoints. So we're going to look at f of -1, f of 0, f of 1, and f of 3. So again, the -1 is an endpoint, the 0 is when f prime of x is undefined. This 1 is coming from a critical point we found, and then 3 is another endpoint. So we're going to evaluate f of -1. So that's -2 minus 3. which is -5. 0 minus 0 for f of 0. 2 minus 3, which is -1. And then if we plugged in 3 into f, we're going to get 6 minus 3 times the cube root of 9, which is about -2.41. So your absolute min in this case is going to be -5, and this occurs at x equals 1. And then your absolute max is going to be 0. That's your largest y value. And this occurs at x equals 0. And then that's it for that question. So go ahead and try example 6 on your own. There's a little more algebra to figure out the derivative because you do need to simplify it as much as you can. But after you've done that, you can follow the exact 3 steps: finding the derivative, setting the derivative to 0, and then plugging those critical points and the endpoints back into the function to see what the y values are. So go ahead and try that and press play when you're done. All right, so here's example 6. Again, like I said, it's pretty lengthy. To simplify f prime of x as much as you can, you are going to use the quotient rule over here. And then once you've done the first step, you're going to simplify the numerator as much as you can, and then simplify it again. In terms of undefined values, there are no undefined values here because we can never get x squared equals to -1 using real numbers. So we don't have any undefined values. Then we're going to set f prime of x to 0. You're going to move things around and start solving for x. And then in the end, you will get x equals plus or minus 1. Step 3 is to evaluate f at the endpoints and at plus and minus 1. You're going to get an absolute min at -1 when x is equal to -1, and the absolute max is 1 at x equals 1. And then that's it.